Okay, we're back as usual. Any questions about the homework, quizzes, anything else? Any logistical questions? All good? Everyone is on board. That's excellent. So then just quickly reminding you where we are. So I get it. So I keep repeating the same stuff over and over. So we looked at what's inside the process, right? Our ultimate goal is to start running a process eventually, right? It will take us a couple of weeks, maybe past the midterm. But okay, now we know what's inside the process. We know that main lives in a code section or text section. Global variables live in which section? Whoever is talking should tell me right away. Okay, where do we have global variables? Which section? Data, good. Local variables are on a stack, so we need to how to assemble those things together. We looked at linking and loading and said, okay, look, we got it. So you don't want to rewrite the printf every time, or a memory allocator for that matter. And so we're gonna just get them as ELF files from elsewhere and merge them together and start running, right? But now we want to think about how to create an environment in which the program will be running, right? So, and specifically how to create a private address space in such a manner that programs cannot interfere with each other, right? And for this reason, we're going to look at these two mechanisms, segmentation and paging. So I'm pretty sure that you guys, you've heard of paging already, right? So it's always mentioned. I don't think anyone knows what segmentation is on x86. However, the trick is that you cannot enable paging without enabling segmentation. And that's why, okay, we'll spend some time looking at segmentation first, because the stuff which we'll be running is real. It runs boots on real hardware. So you do need to understand segmentation in order to enable paging. And other reasons for why segmentation is suddenly important is that in the last decade, all modern CPUs started rolling out mechanisms which are kind of similar to paging, not always, no, to segmentation, not always, and they're different, but the only goal is to kind of say, we're good with paging as an isolation mechanism for a while, but it's just too slow for modern needs, and we need something else. And literally, there are papers from top schools within the last 5 years which advocate for the mechanism, which is segment-like. And does anyone need to, we're going to talk about it more, but the industry driver to ask for segmentation is something what is called WASM, or WebAssembly, right? And you heard of it as well. We're going to talk a little bit about it today, just to make sure that we understand what it is. But okay, segmentation is coming, so it's not like some archaic thing which I decided to teach just because whatever. It's real life, and you'll see it soon, in a professional life as well. Okay, cool. So our goal, remember, our high-level goal is to write this yellow piece, which we call the kernel. And in the end, this yellow piece enables us running multiple programs, right? Apache web servers, web browsers, shells, whatnot, right? We have a question here. So in the end, when you have a CPU, you have one physical memory, right? So you have multiple DIMMs, which you plug on a memory bus, right? But they provide an abstraction of a single physical address space. It starts from 0, goes to 64 gigabytes, for example, right? How can we run multiple programs on one single memory? What can be an idea? How can we do this trick? Virtual memory. So what is virtual memory?
It acts as memory, just makes it so that you can more easily just access it chronologically without it happening.
Correct. So virtual memory is that at a high level, is if you have some kind of an address in this register EIX, let's say EIX contains value 55. Instead of directly accessing this physical memory at location X55, we'll come up with some kind of a mechanism in between which changes this address or translates it according to the rules which are set up by the kernel. So maybe it does addition of some base, for example, meaning that if base is 1 megabyte, then the address will be 1 megabyte plus 0x55, right? And this is similar to segmentation, kind of at the base. But you can come up with different translation mechanisms. You can say, look, I will be translating at a granularity of something what will be called the page, which is a 4 kilobyte. And there will be, instead of this cloud and a single like idea of adding a base, there will be like a real radix tree sitting here, which hardware will be looking up, and for each instance of this address, like for example, for x55, will follow the translation, and who knows whatever the value. It's configured by the operating system. So that's virtualization of memory. That's nice. You kind of hijacked my conversation. But if I say, okay, I want to build the cheapest, the smallest, the simplest CPU ever, it means people like my whatever, they came back to me and say, look, this is too expensive, too much silicon. This is like, this tree, forget about it. We cannot fit it on a die because the chip is so small. Maybe it just harnesses energy from the environment. There is no battery, for example. There are those chips, right? And it matters how many cycles and how many transistors are run on this chip. So if I ask you a question different, and you say, if you don't have virtual memory, although it's a nice idea, like for desktop, mobile, and everything is used, right? How else we can run this? How else we can implement this idea of running multiple programs on one physical memory? Sure, yeah, that's a good idea. And I just wanted to make sure that we understand these options. So here on a slide, we say, look, maybe we will be running one program at a time. And it will occupy this address space from 0 to whatever max address. And when we switch to another program, we'll just either throw this away completely. Maybe it's a batch processing system, or maybe we're going to save it to disk, right? It's not fun, and it already feels artificial, right? Because it seems like the loading something from disk will take us more energy than doing something lightweight. But still, it's an option. I agree with you. So how can you split the memory in two? Correct. And do you know the machinery for how to do that? Like literally, imagine this is a shell program. This is WC. How will you, like, if I ask you as a homework, and I said, like, which implies that you only need minimal knowledge and that you already have it. How will you do it? How will you split it? Like, what is involved? Well, caches are more like a hardware abstraction to speed up memory loads. You had an idea?
Just have an offset that storage for each program.
Just have an offset for each program. And I agree with this. But what I'm getting to is that we just covered this idea of relocation, right? So offset on its own will not cut it. You need a little bit more. You need all the like data accesses, like global variables, heap accesses, and everything else to be with an offset, right? And we can build it. We can say, look, even if we have the same instance of the same program, like 2 shells or shell and WC, we can do this trick with relocation. We already know it, right? So that's what I'm saying, that if someone comes to you and says, okay, like, this is the task, like with the minimal amount of hardware support, implement this idea from the operating systems, which allows you to run multiple processes on a single physical memory, you say, sure, I get it. So I understand that each process internally will have its own process text section, like green and yellow. The font is a little small here. Private data section, maybe heap, which is growing this way, and maybe a stack, which is growing in the opposite direction. And you say, like, I know that, like, if you give me a compiler and a linker and everything, I will relocate. And one program will be running from address 0, and a second one will be running from this address, whatever it is, 1 megabyte plus something, right? That works, right? No virtual memory, no hardware support on any embedded device, which like, okay, 8-bit microcontroller, which you use in your robot vacuum or something, go for it. It will run, right? And it will build beep sounds, maybe play music if you like, right? Make sense? Will it work? No hardware support. 2 programs, 1 memory. I wanted to understand that, okay, it works. And in my example, it's the same instance of the LS program. That's fine, but and as I was saying, that works, but it might not be ideal for all of these scenarios. And what do you think is the problem here, or what is not ideal? If we like switch back to this slide to think for a second. What he's saying is that correct. I agree. So what you're saying is that there is no idea, like back to this idea of virtualization of memory. And in fact, this idea of paging, it came out from the idea that you really don't have that much physical memory on board. And so you will virtualize it with the disk space, meaning it will be taking parts of the program out to disk and bringing them back in memory. And I kind of claim you can do the same trick. You can, as you were saying just a second ago, well, if I want to run a third one so badly, I don't know, maybe someone came to like, I want to play Quake on this, like on this vacuum for whatever reason. Maybe it's a bot and you play laser tag or something. You can kind of like swap it to disk, right? So it's not ideal, but it's doable if you, and again, it's nice to discuss the space of the solutions like and craziness. So like worst comes to worst, you can save it to disk. It's not that bad. What else? What else is not ideal about it? Yeah, and you're right. So by the way we constructed this address space, it seems that there is some awkward gap here, which just seems wasted. And also there is kind of like a hard limit on top, and who knows how to go about it. So it's not very flexible. I agree with that. I'll talk later about how to resolve this flexibility or inflexibility and make sure that, again, there are ways around it, but not ideal. I agree with you. But again, like I kind of want to point the main problem with this design. And especially this became important in the last 20 years, maybe. For the first 10 years of computer science, it wasn't a problem at all.
So the chunk is big, so maybe you cannot, like, there's no flexibility to have a little bit of like memory.
You're right, but you going back to inflexibility of how to like make sure that we don't have this gap, or what if we're running out of space? And I kind of can say that maybe there are ways around it. I'll show you later how to do it.
No isolation.
There is no isolation, right? So like since you and I was expecting isolation being an answer right away, but it took you a moment. So like you think isolation is not important, or why no one suggested? Do you understand what does it mean, no isolation, in this specific example? You don't, okay. Anyone?
Does it mean that like from your first process, you access memory, the second process, if you change?
Correct. And just to be specific, since you said I don't understand, and I don't expect you to understand, let me just give you a better explanation. Imagine like in your process text section, there is a move instruction, which uses an address inside EAX. And under normal conditions, EAX points to the data section or maybe your own heap, depending on what the semantics of the program is, right? But imagine you somehow either get this value, like for simplicity, let's just say from a printf function, or maybe you receive it from the internet, or compute it based on the data which you received. So maybe someone says, okay, I sent you a buffer. Here's a buffer, a packet. And you say, like, normally packets are 1 kilobyte, but some person on the other side of the planet decides to joke and says, okay, I'll send you 1 megabyte buffer. And if your code doesn't change for the bounds of it, right, says, okay, I cannot process 1 megabyte packets. Like it's a realistic example. This EAX suddenly starts pointing somewhere over here, right? Because you wrote your code in C, for example. It blindly follows, okay, read the size, 1 megabyte, assign it to EAX register, and then do this load, right? And you end up either reading, or if you're saving in a buffer, overwriting the memory of another program, right? Or maybe the kernel, which sits here itself. In a modern language or terminology, this is called a vulnerability, meaning that your program is vulnerable to this specific exploit, which allows you to access memory of another program. To make a concrete example why it's important, I keep bringing it up. Imagine this is a web browser which accesses your bank or something, or does some other financial stuff, which is like which is connected to money. Maybe you inputting the credit card in somewhere in the form, and this form is saved as a struct foobar here. And this is another web browser where you loaded a page, and your lovely professor controls this page and just reads your bank account, right? So that's a real problem. But there is a variety of those. Like attacks became so prevalent that people attacking like nuclear enrichment facilities in other countries, right? Attacks became government sponsored, right? So we have government agencies which work on like offensive and defensive security. And there is a huge probably at this point, billion malware economy where people are paid money to discover those vulnerabilities just to steal the credit card information from other people across the globe and then resell them or whatnot, right? But it makes sense. So I made an example of this one register EAX, but you can imagine something like move relative to ESP, for example, and someone says, okay, look, allocate a giant buffer on the stack and you didn't check the size, and your stack maybe spills over, circles around or something like that and covers this area, for example, right? If I ask you, okay, do we understand at least at a high level? I don't know, like how many people understand those attacks in general? Like it's not covered in CS curriculum up until this point, at least, right? Okay, but you kind of like, the beauty of this class is that it's so bare bones that you say, look, I kind of got it. You compile the last, you read the size of the buffer from printf, and it can be anything, and then it's an exploit, right? And we'll see more. Okay, so isolation is important for those pragmatic reasons, right? And so essentially, the way modern operating systems are structured is that they implement this red boundary. So one program cannot access memory of another programs. And of course, a program cannot access the memory of a kernel, because typically the kernel is responsible for enforcing this boundary itself. And the moment you control the kernel, you control the whole system, right? So, but we need these two boundaries. So any questions about this, about the need for isolation? And also any questions about what isolation means, at least at the level I explained it. But feel free to ask more questions. Like, for example, you can ask a question like, what if you run Java, a safe language? Will all these bugs disappear? Or my ideas about like, accessing an object out of bounds, for example? Yes or no? Some people are hesitant. Java is a safe language. It can be done in software, yeah. Can software have some protection? That's what I'm trying to ask. So for example, safe languages. Do we understand safe languages? Like, for example, go ahead. Okay, so safe languages, it's a great kind of idea. In a safe language, like in C, for example, you can say something integer a array of 10. And next time you say a, let's say 11 equals 5, the compiler happily passes this program. It says, okay, wow, I don't check for memory sizes of objects on data or the heap or stack. Whatever you do, it's almost like assembly. Access any memory you like, right? Especially if I put here, instead of 11 here, I put something like an index I, which depends, for example, on the input to the program. Then in C, it's a wild write. So you do whatever happens, right? In languages like, in safe languages, like for example, Java or C#, there are rules of safety, meaning that every time you dereference an object like A, which sits on a heap, so this is A, the compiler will insert enough checks before this operation to check that this access is in bounds, for example. So meaning that if it's an I and the object had the size of 10 and I suddenly is 11, at this point, there is just simply enough code in front of the memory access, which compiler generates, that it says, well, it's an exception. You're trying to do something and it's unsafe, meaning that you're trying to access memory out of bounds, meaning that maybe there is like object B allocated here and you're trying to read or write B, and that's not okay, right? And compiler specifically enforces the following rules, that you always access objects correctly to their types, meaning that you access A as A, not as B. It's called type safety. It enforces spatial safety, meaning that the accesses are in bounds, meaning that this check is that A is only 10 elements and you don't access like element number 11. That's spatial. And also it enforces temporal safety, meaning that this object is still allocated, meaning that in Java, you run a garbage collector and this A will never get deallocated before you drop all the references into this object, right? Do you agree with this? So there's three major, but you can come up with other safety rules like race freedom, meaning that you're not accessing this object, stuff like that. But the first three are probably the most important. And languages like Java, Rust, C#, well, Python as well, they enforce those rules, obviously, right?
So is it after
Well, the question is like, what is it we trust here? Do we trust Java compiler to implement all these rules correctly? Do we trust the libraries which Java runs underneath, like to implement printf? And maybe for whatever reason, they said, we do not implement printf in a safe subset of Java, but instead start using C-like extensions, right? And that's essentially what I'm trying to say, that like, I expected actually that you guys know more about safe languages, and I thought that, okay, and immediately a person would ask me, okay, in a safe language, this attack is impossible. To a degree, yes, but there are bugs in safe languages because it's a huge compiler tool chain which you have to trust to implement all those rules correctly. And also there is the library ecosystem, which is almost impossible to build in an entirely safe manner. So occasionally there are bits of unsafe assembly-like code even in Java, and those bits are exploitable. Although in general, safe languages protect you against those like simple out of bounds accesses, liveness violations, stuff like that. But so maybe it's too much to the side, but I just wanted to make sure that we at least understand something about it.
correct? Obviously, you're running a C code, you can still hit segmentation. And I guess my question is like, at what point does the operating system start to play a role and the process is not accessing each other?
Right, and that's the topic of today's lecture. Let me get to this. So what I'm saying in this example, if we just simply use this trick with relocation, but no boundary between these two, and this boundary can be enforced in hardware or in software, as I will argue in a second, there will be no segmentation fault. If you have a bug which sets this EAX pointer to point to another process, unless you provision some kind of a protection mechanism, and I'm not discussing it right now, this access will be allowed, right? And in a safe language, majority of those accesses will be taken care of by the language, but I'm saying that there is still like layers of trusted code inside Java, which is at some point also gets compiled into machine instructions, which we are looking at, this moves, which also may contain bugs. But that's essentially my point of today and tomorrow, or not tomorrow, but Thursday, is to explain you what kind of segmentation means. And as we go forward, you will explain, the explanation gets more and more concrete. But we are starting. Okay, cool. So we got the point that the relocation is a trick. If you really need to run a vacuum and no one will ever attack your vacuum, you can run the two programs, one which, whatever, navigates the vacuum, navigation software here, and another maybe plays music, like MP3. I don't know if you want to listen to your vacuum, but whatnot. Maybe it's an alarm, you know. Fine, but isolation is a problem, right? And we spent some time discussing it, right? So, like, we say, like, my discussion was to set up the stage for this question. Like, if we want to enforce isolation, like this red boundary between multiple programs and programs in the kernel, how can we do it? Like, what mechanisms we have to ask for, either from the compiler or from the hardware designers? Okay, no, I agree with you. So you say, look, I have a move instruction, it accesses EAX. Are you suggesting to do kind of like a check here in front of this EAX access, right? And I agree. So, and what you're saying is that, like, can we call into the kernel and ask this question? Is this access allowed? Like, is it in bounds, right? And at a high level, I agree that yes, this is the answer. But the only difference from what you said is that instead of like asking the kernel, because asking the kernel might be expensive, but in a way, like it depends on what you call a kernel. I agree that instead of kernel, let's say a layer of trusted computing base, which people call TCB. In front of every check, in front of every move instruction, you say, look, let's run a check if this address is in bounds. So for example, from 0 to whatever was our example, 110000, right? Agree? So how can we enforce this check? That's a great idea. What you're saying is that you can ask the instruction set to be so fancy that it does the check automatically underneath, right? So essentially you ask for hardware support. And I will cover it in a second. This is the idea of segmentation and later paging. So essentially those checks are implemented in hardware. But just for the, and it's right idea. But can we do it in software? Correct. So you can say, look, we can use compiler instrumentation. Maybe we will reserve a register like EBP, because we said, okay, EBP is only like somewhat useful. Instead of maintaining the frame, maybe we will maintain some kind of bounds here. Or maybe if we need two registers, EBP and whatever, ECX, for example, let's use two registers and then do the check in front of every load and store instruction, in front of every push instruction, right? Stuff like that. And this idea is called software fault isolation. This idea was pioneered, like, let's say, 20, 30 years ago, essentially inserting the checks at compile time or later at binary rewriting. Then it came back with a Google Knuckle or a Chrome sandbox, let's say 15 to 20 years ago. And now it's actively used as part of this WebAssembly technology, which allows you to run a real C code on the edge of the network, like roughly speaking, within the browser. But the idea is the same. And you say, okay, like, why is it even interesting? So I wanted to just for a sec just show you a demo of why it makes sense. When I was a kid, like Quake was still the thing, right? And it was a little hard to like get it running on lab machines. We didn't have root passwords, nothing like that. But this example shows you, and when I was a student, it actually showed up as part of the Google Knuckle. It allows me to play Quake inside the web browser. So specifically, this is a Quake WASM. So it uses WebAssembly. And if I say start Quake WASM, well, it runs. Right, man. Name. So I can play, and okay, it runs. It runs within the web browser. I don't know how impressive it is to you. It was impressive back then. And it entirely uses software fault isolation. No hardware support, just those checks in front of every move and store instruction. So as a human on a powerful machine like this Mac, I don't even notice, right? So if I ask you a question, like more concretely, like this is a tiny little program. And it's actually a poll time. Let's brainstorm how we can enforce soft isolation and software on this tiny little program. And I will go to the poll software to enable it. Yeah, that's me. Here it is. So you know, like by now the URL is familiar. How can I present? I can present it like this. Well, let me maybe reshare. I'm not sure what I'm sharing. Share. Can you guys respond? Do we see the responses? I never ran this type of activity before. Oh, hardware design. Okay, cool. So, well, to be more specific, in software, so hardware design probably should immediately ban right away. And just before going there, I wanted to put up this program. Again, despite the fact that, you know, I talk a lot, I might be like a little like imprecise. I want you to figure out, like, for example, there is a move instruction here. What do we need to do in front of this move instruction? There is a push instruction. Is it a good instruction or dangerous? When there are more move instructions, and they use EBP as a base, even more move instructions. Do we need to do anything with those? Do we do anything with the ret instruction? The question is a little bit more sophisticated or complicated than you think, although I obviously just judge on participation. But you see the problem. I was illustrating my software isolation story with the move instruction, but clearly there is more to it. There is clearly going on something. And each of these instructions should be taken care of. Okay, let's go in class one by one. So is this one a benign instruction, or we have to do a check here? Yes or no? A check, right? Because we're pushing, and this push is relative to which register? ESP, correct. So we need to do a check of whether ESP is in bounds of our, if we want to be precise, in bounds of the stack segment, or just in bounds of the entire address space if we don't care if the stuff like maybe it's goes from 0 to, in our example, 110000 or whatever the address I was, right? So we have to insert a check in front of this first instruction. What about this one? Move. Or it's just even like updates to registers. So we can, as a design principle, we can say, look, whatever. If they want to change registers, let them do it. We don't care. Only when we access memory, we will check something, right? So no checks here. This one, reserving space for local variables. Yes, no? Fine or not fine? But we're not overriding the stack. We're changing the stack register. If we agree that we're going to check every memory access, like a push or a move, we can say that temporarily we can allow any value inside the SP. Although technically speaking, if you go too far into this field, you can say, look, I will enforce stricter rules for different reasons. Maybe it will give me better performance. So you can go either way, but let's, for the sake of simplicity, say do not check anything here. So here is the move. So obviously we're going to be checking, right? So we say, look, this address EBP minus X8 should be in bounds, and we will insert a check. Agree with this? And the same for all other moves. This is operation on the registers, so we don't really care. This restores, I think it pops something from a stack, right? So it pops into EBP. So this will have to do the check. Because leaf touches the ESP, so we have to check that maybe we overrode the ESP here in such a manner that it points somewhere. So we need to do a check. What about this rat? Was it checked? Rat, if you have ESP, it maybe your return address is right here on a stack. What if we change the ESP to point to somewhere else? Agree, we need to check in front of return address as well. So which means that I was talking about those were like data accesses, but this rat is a control address, meaning that it's a control flow instruction. And in a well-formed program, you need to ideally preserve the control flow. Otherwise, you start returning elsewhere, and then you can do different interesting things. Is that clear, this return address? And one specific attack that you can, in fact, return maybe, if you have a check in front of this push instruction, maybe you're going to return right past the check, which means that at this point, you screwed the check completely, right? Because one thing which you have to enforce is that no matter where you return, you will never return in between the check and the instruction itself. Agree with this? The question is like how you construct this check, right? And intuitively, one would want to see something like a segmentation fault. So you just either call to the operating system saying, okay, if there is an illegal access, so then terminate the program, or you like along those lines, essentially. It's up to you how you want to build it. Typically, you use some, like on x86, there is an illegal instruction which triggers an exception, which is passed to the operating system. But if this instruction is not available, you can just explicitly call into the trusted computing base saying, okay, there is a illegal access, so time to terminate this program, right? Does it make sense? So those checks. So two main flavors at a high level, just data checks relative to this, like accesses on the stack or in the data or heap region with moves, but also control checks to make sure that we at least cannot jump past the check, right? And that's fine. So let me quickly close the activity. But maybe we can actually maybe take a look real quick at what people voted for. Where is this web browser? It's already gone somewhere. Let's just see what our results were. Oh. Well, so this is this is a good answer. So pretty close to what I was discussing, and it got 2 votes. And oh, containers. Okay, containers, Docker, stuff like that, like seccomp is a different technique, but yes, we're talking about sandboxing. Containers rely on hardware mechanisms. Memory protection, well, idea was to use software. But anyway, so I appreciate your answers. So hopefully it triggered at least some discussion and some thought process. Okay, this is disabled at this point. Okay, back to the lecture. For a second, Just wanted to make sure that we understand it and that I'm sharing the right slide deck. That's cool, yeah. So it turns out, as I was saying, in the past couple of years, this idea was forever impractical. Those checks were super duper expensive because if you really compile the code as if a register is less than an upper bound, greater than the lower bound, those two jumps introduce you, like, it's too many instructions. Overheads were astronomical, like 2x, 3x overheads. Not a practical idea. And then people from Google were among the first ones who pioneered essentially faster checks. And the idea was called native client. And if I ask you a question, okay, how can we do those checks fast? And how fast they can be? And you saw the Quake running, right? Which may not be convincing, though. You need what? Correct. So ideally, yes, you need hardware support, but what if you don't have it? Can you do it in software? How to do those checks fast in software?
You're like a really smart compiler.
Correct. So if you, for example, have a loop or multiple accesses, you can reorganize instructions and check once, and you track the dependencies, and then it's yes. And WASM compilers do this as well. But still, there will be a fair amount of checks because every fifth instruction, I think, according to like architecture researchers on commodity programs, like whatever stack, is a load or store instruction or memory access instruction. So in front of every fifth instruction, you add those a couple of jumps and whatnot to check upper and lower bounds. So the question, can you do it faster? Can you come up with the trick at the level of assembly to do it fast? And this is what WASM compilers are doing today. That's the only reason I'm teaching it, is that you go like interview at the company and they ask you, do you know something about WASM? Hopefully at this point you say, yes, I got it. So finally the guy told me. Or if you like even didn't get what I'm saying, you can quickly look up the papers and get this understanding. At least you will have some kind of an anchor in that field. So how to do this checks fast? A trick, any tricks? Like, okay, naive check, just to be concrete, naive check. If whatever access EAX should be greater than, let's assume we have two registers, I don't know. Like I'll name them R1 and R2 just for the sake, or even like RL for lower bound and R high for high bound, right? But you can pick any registers. Your compiler can pick anything what you believe is appropriate EBP, if you don't want to use it, and ECX, for example. And you say EX less than R high, and EX is greater than R low. That's kind of the check then. It's okay. Else, exception. And the question is how to minimize this sequence, right? Because those two checks will be compiled into some kind of a CMP instruction comparison, then some kind of a jump when greater or less, greater, and another CMP, and another jump when greater, for example, depending on how you compile it, right? So it seems like a fair amount of instructions, right? The question, like, can we minimize this for two comparisons and two jumps into something smaller? And what will be in the table? You can keep those like upper and lower bounds there in a table. People usually put them in registers to avoid an extra load from a table, although you're right, so you can use a table as well. But any ideas for how to implement those? Okay, enough talking. So the example which they came up with, which is kind of pretty cool, is the following. So imagine you have on 64-bit machines, for example, RAX is 64-bit register. We restrict the allowable address space to just 4 gigabytes, to the lowest 32 bits. So everything in the upper bits, like, doesn't matter to us. Then we designate it turns out that if you do this instruction like move EAX, despite the fact that you had some values like OX, FF, something in those bits, if you just save the result in the 32-bit registers, it clears those bits. It just resets them to 0, right? So roughly speaking, if you say, look, if I can do this move in front of my real move, I can really like make sure that everything is limited to this 32-bit values, and which means that's from 0 to 4 gigabytes. And then what you do is that you say, look, I will designate one register to hold this segment, like a number, essentially. An idea is to place this segment into the upper bits of those registers, right? So you kind of like say, if you do this operation after you clear those bits, and you say, look, RAX plus R15, you will get the real address inside RAX. And that will be your essentially, that will be your target address. So it's essentially like the address space is split into 4 gigabyte chunks, and this is like the number of the segment, 1, 2, 3, or whatnot, right? And essentially it can compile into something very simple like this. So let me erase the link on the slide. So you first say, look, in front of the load, in front of the real load is relative to the RAX address, right? You clear the upper bits of the RAX by doing this EAX to EAX, and then use RAX as an argument in this move instruction, which uses R15 as a base, adds RAX in this example plus, I forget what one stands for, maybe nothing. And then you load into the RCX address. So instead of like doing 2 comparisons and 2 jumps, we really introduce a single move instruction in front of the load instruction, right? And that's not bad. You say, look, like it's pretty fast. It's just like one extra instruction here. What essentially the trick which you're observing here, instead of doing a proper check, we're simply masking it. We say, look, whatever you had there, we will erase it with zeros and then overwrite with the value from R15 register, which contains the segment. Is this trick clear? It doesn't work that nicely on 32-bit machines, but as we see later, 32-bit machines have segmentation, but 64-bit machines don't. And that's why modern compiler like WASM use this specific trick to mask, right? Does it make sense, this masking? In front of loads and stores. If the program is malicious, then what?
They will fail.
They will fail because if this RAX points to like elsewhere, to the kernel, for example, since we masking the upper bits and enforcing the, like, let's say, for sake of example, 0 here, then the load will go from the first 4 gigabytes, right? And it cannot escape. So no matter which value you put into this register, the actual load which we're performing here will be contained within from 0 to 4 gigabytes, right?
Is the question then whether?
Correct, and a great question. So how can we enforce the fact that R15 points to like that attacker cannot change this value, for example, right? How can we do it? It can be done at the level of a compiler. So for example, you say, I will change my C compiler to make this register invisible. It's only visible to the trusted computing base, and normal code will never touch it. And which means that attacker, no matter what you do within your code, you cannot change the value of R15. It can also be done at the level of assembly with a binary rewriting. You have to change the instructions slightly. But compiler pass, LLVM compiler pass is really easy. You say, imagine the architecture like x86, but R15 does not exist. Everything else is compiled in anything but R15. And then R15 is only designated to like privileged operating system accesses, which set it. Make sense? But great question. Yeah.
And that can be set by, for example.
And the operating system. Yeah.
And then the first move instruction, what it's functioning is it's just like enforcing
Correct. And it's enforcing it by using a mask, by masking the upper bits. Correct. Yeah. It's a clever trick, and it runs pretty fast. On ARM, actually, there is an explicit instruction. This instead of doing this trick with with move ex on ex, you just there is an explicit bit field instruction which says, okay, I will take the lower bits from x10 and we'll take the lower bits from x28 register and combine them in such a manner that it actually like puts the segment on top of the like x10 bit. So it's like an explicit instruction. So it's slightly cleaner than on x86, but the same effect. And surprisingly, this trick works pretty well. So like I have a collection of benchmarks from a spec 2006 and 2017 benchmarks. There is a bzip compiler, libquantum, who knows what it does, like, but it's like stock benchmarks. To be honest, it's done by my team, so like not all the benchmarks we were able to compile, but you can see that it's normalized to 1, to like unsafe C, and it like sometimes like a couple of % overhead. On average, it's 18. On x86, it's average 17.4, right? Same idea, slightly different set of benchmarks. And that's why you're seeing me playing the Quake, and the Quake runs maybe 17% slower, but you know, with enough powerful machines, it doesn't matter, right? And so this is the trick which WASM does. So just make sure that you remember, WASM is important. It's used in production. It's coming, rolling, and you will see more and more of it. I'm just, and the whole idea behind WASM is the software fault isolation. So essentially enforcing those checks in front of every load and store. Good. On SFI, software fault isolation question.
The lower bits.
Yeah, the lower bits, you structure your address space as you say, my process number 1 starts, let's say, at 0 and can go up to 4 GB. In practice, there is a gap because you think you can double. There are instructions which allow you to access the second 4 GB region. So you put a gap here, and then the second process starts from here. So this is process 1, process 2. And if it was 8, like from 4 to 8 GB, everything is 4 GB regions. So this from 8 to 12 will be a second process. And this address RAX can point anywhere within this segment, which is not ideal. It's kind of like unsafe C. You can overwrite your own stack. You can, ideally, you cannot overwrite for sure, you cannot overwrite your own data, code section, because then you can elide the checks, right? So the code is probably mapped as read-only or something like that. Or you like separate them.
I'm just wondering exactly what this stuff actually happens. Like it's usually going to happen a lot of them, right? When the process is loaded, or it's like
Yeah, and all of this is possible. So WASM typically does it at compile time. Well, I'm pretty sure there are like just-in-time compilers. NACL was working at the level of binary rewriting. So you take it, they wanted to have binary compatibility, and you say, look, we will take a binary which you already compiled and then do the rewriting statically as a post-compilation step. But I'm pretty sure that you can do like a just-in-time compilation as well. It's probably less elegant, but all of these options can work. WASM is compile time. You really compile into something. Any other questions? Okay, good. So everyone is like, man, like we didn't expect you to talk about WASM for so long. And so at this point, we say, well, we got it. You can do it in software, but we trust our hardware engineers. And instead of all this nonsensical software fault isolation thing, let's just ask for the hardware support. And so if you were talking to a hardware engineer, what kind of support do you want to ask for? What is the hardware feature? You said, change the instruction set to do X, Y, Z, change anything. What is that you want to change? Yeah, that's kind of like That's why I was willing to spend so much time to explain this idea, that because if you just look at it from the hardware standpoint, you say, look, it's magic. But in practice, this is exactly what you wanted to do. You can say, look, guys, I just want to like kind of do this check, but in hardware, in front of every move instruction. As you say, like enforce the bounds. And that's exactly what the hardware is doing. So that, let me just scroll really hard here. So they say, look, we will essentially make sure that for each process, we'll keep track of some base address. And literally, we'll be just adding those base. The bases are configured by the operating system, right? And you say that if you have an address X within the address space, it will become X plus base. And as well as, by the way, we will check for the limit, for the size of this. It's not just a base, but it's a base and a size. And no matter which address you issue here, it will always be like limited to this green physical region of address memory, right? It's exactly what we were trying to do in software, but now hardware designers said, okay, let's do it in hardware. So meaning that you have to, if this address X is X55 in one program and the same X55 in another program, because the bases are different, obviously, they will land at two different physical addresses in memory, right? So we're virtualizing memory. At this point, we say, look, we don't need to relocate anything because every program can start at address 0, right? So data section starts at 0 or the code section, and we will just, the operating system will correctly set those bases, right? I agree with this trick, super easy, right? So it's exactly like a segment, which we just seen in software, right? And this is exactly what the CPUs are doing. One question is like, where does the base address come from? There is a variety of design choices. You can say maybe we'll have a set of registers which operating system sets, but x86 does it in a way, in such a way that it maintains a table. So this idea was showing up earlier, a table of base addresses, right? And there is a special register which indexes into this table. Let me just go through more detail. So there is a new register which is called a selector register, which is nothing but an index in the table. So the operating system configures the hardware register. This table is called global descriptor table, or GDT, on Intel. And there is a hardware register which points to the base of this table, GDTR. Operating system sets this register. The idea is that the program cannot reset this table, this register, because it requires a privileged operation and the user level code, which we will cover later. If you try to invoke this instruction, it immediately causes an exception. And the operating system also hides this table in such a manner that the user code cannot override the entries in this table, right? But that's what x86 is doing. So essentially, more concrete example. So we have physical memory. It starts from 0, goes to some max address. We have a instruction. I'm using AT&T assembly here. So it loads from the location in memory pointed by the EBX register into the ACX register, or EAX register. EAX register is currently 0. EBX is this value. So essentially, normally, and we have value 55 stored in memory. Normally, this address would go directly on a physical memory, but here, like the operating system maintains a table. So essentially, okay, let me scroll here. The table is called global descriptor table. It contains, the CPU offers multiple registers to use as indexes, like code segment, stack segment, data segment, and a couple of general purpose segments called ESFSGS. For example, if it's a data segment, since we're using a move instruction uses a data segment register as an index, it equals 1. So we pick entry number 1 from this global descriptor table. By convention, entry 0 is not used, it's invalid. And so essentially the value here is 110000. So instead of this address, we add the base. Let me show you here. So we take this address 110000, use it with the base. So if we were issuing, if it was 0, we would get this address, obviously, and this is where in physical memory we have it. But everything is shifted. So if we have this address, we will get 41 instead of 31, right? And this global descriptor table register points to the location in physical memory here where this table is configured, right? And it's placed outside of address space of any process. Only the operating system itself will have a segment which allows it to access this table. Make sense? That's segmentation. That's the same idea which we were talking about in software, but done in hardware. All these registers are real. If you want to boot an x86, you really have to configure them correctly. And obviously, if you have your second process, you have options. You say, look, I will either use a different global descriptor table, like green process will have its own global descriptor table, yellow process will have its own yellow global descriptor table. They will be different locations in memory. And when you switch between process to process, the operating system can switch between these global descriptor tables by updating this GDTR register. So instead of pointing to a green one, it now points to a yellow. Or, as we will see later, x86 instead, just instead of switching between two physical ones, just updates the values within the table to make sure that enforces a specific limits for each process, right? Make sense? Okay, so it's, yeah, question. Well, in this specific example, this register, GDTR register, is per core. So if the same green process will be running on a different core, maybe there are two threads, right? For example, they run at the same physical time, then GDTR on this CPU will also be pointing to the same physical address, so they can use the same. And if one core suddenly switches to yellow, obviously yellow starts running on this core, then this GDTR will be pointing here, but the other one can stay pointing to green, right? We'll talk about how multiple CPUs work later. Okay, makes sense. Let me cover quickly some details. Like at a high level, it's a very simple idea. The devil is in the details. It's not a very hard concept. So Intel introduced, they call it a logical addresses. It's a new addressing mode, not physical, not virtual. It's called logical. Intel is good with different acronyms and names in general. So now all addresses are logical addresses, but a logical address consists of two parts. One part is effective address. That's the actual thing which you put in register, like EAX, for example. And the second part of this logical address is in this segment selector register, like CS or DS or whatnot, SS, right? Those are different registers. Outside of those 8 registers, which I was talking about, those are new registers, right? Which we've never seen before. And literally this registers, segment selectors, they work as indices into the global descriptor table. And from here, you read the base and limit. So the base is just added to the effective address, and the limit is checked to make sure that you're not going beyond the limit. And this produces linear address. And in case that if you don't have paging enabled, if you have the paging enabled, then this linear address will be forced through a page table translation. If you don't have paging enabled, this linear address is actually going on the memory bus, and it's actually like a physical address. Make sense? Okay, not super hard, but it looks weird. But if you were the one to design a CPU, and we were designing a CPU 2 weeks ago with my students, and we wanted a hardware extension which is segmentation-like, but better for isolation, faster quake in the web browser, stuff like that, or more quakes in a single window. So essentially, to get rid of those 17% overhead, you eventually converging to a similar kind of data structures. If you're hardware design, it looks very, very intuitive. So we have the table. Each entry in this table, in this global descriptor table, we will see later when we start booting the operating system, there are multiple fields, but at a high level, we only care about those 4 sets of things. I keep mentioning the base, so essentially the base of the segment, the limit, actually the size of the segment, Intel calls it a limit. There is some historical thing why. Access rights, it's kind of meaningful. So the segment can be executable, can be readable, or can be even writable, right? And you can control those to protect the code, for example, from being overwritten. And also it encodes the privilege levels from 0 to 3. And I'm pretty sure that all of you heard of this privilege levels on Intel, right? Or rings. Rings are actually kept in this global descriptor table. That's why I'm saying if you want the rings, you have to enable segmentation, right? So you're not going to fly without it. That's why we teach it. I teach it here. Okay, so we covered all these ideas. So we say this is clear that this effective address, if we have a move instruction, which loads something from the address pointed by the EAX register, so this is the effective address, right? So this doesn't change. And you have to be careful to make sure that DS is set up correctly to point to the entry in the global descriptor table to fetch the limits and the bases, right? So essentially, every time you, in this programming model, every time you issue an address, right, it consists of two parts. So effective address in the register and the base which you fetch from the descriptor table, where selector is an index and the dot base is kind of like a field in the data structure, which is kept in this descriptor table array. I just rewrote my drawings in kind of a C style notation. Clear? Any questions? Is it a recent design? No, I think it shows up in Intel 286 machines, right? So it's I would say 90s. It's not recent. The recent adventure which Intel took is that they disabled most parts of the segmentation on 64-bit machines. Then they realized the mistake, and now they don't know what to do. Okay, so this is the translation. We've seen it. It leads us to this wonderful idea. And if you very carefully like follow me, you ask yourself a question. Look, like really, I always was writing this code. I never wrote anything like DS, SS, DS, SS, CS in front of my instructions or anything like that. What's the trick? I bet that like 99% of people never heard of segmentation. So who heard of segmentation ever before? Or can explain, okay, yeah, I know. That's how I was as well for many years. But what's the trick? Like you never seen anything like this code on the right. You always just write this normal stuff. So how does it work? Although from what I said, it clearly has to be there because I say segmentation is used on like, we're running, okay, this is ARM. Whoever runs Intel laptop, segmentation is on. Any tricks how we can explain this phenomena that we never seen segments before? Right, but that's a great idea. But you've seen my disassembly, right? Like this is real. In fact, I should probably assign something like assign to disassemble. Never seen a move with the DS in front of it, right? How does it work? So, I mean, there is no magic. So CPU said, okay, the CPU designer said that we will imply a segment based on the access, right? And they say, look, if you do a data access, we just by default imply a data segment, DS in front of it. So you don't have to put it in front of it. If it's a jump instruction, then we will imply a code segment. And only if you're so smart that you want to overwrite our decision, you can really write an assembly instruction which uses like CS in front of it or DS. Like you in it used to be that in C it was called a long jump, so that was a jump which like changes the segment, stuff like that. But that's the convention. So you can always overwrite it, but in practice it's so rare. We always assume that data segment only like modern programs use one data segment. Modern programs use one code segment, and modern programs use one stack segment. Operating system configures them. In fact, they even like all of them almost overlap, as we see later, which essentially like you never see a segment. The only like, okay, does anyone ever seen a segment in the programs which you were debugging or disassembling? You see the segments. One segment is used on modern programs or code bases. It's called thread local storage. That's what you wanted to say. So yeah, so this, like you've heard it, like in modern languages, you can say thread local data, right? In C++, you can do it, right? Thread local. And in my explanation so far, I always talk about data segment, heap, local variables. Okay, the question is like, where are those thread local variables stored? And they stored in a separate segment. And the instructions like move instruction will use either ES or GS segment in front of the address. Right. So if you compile the code which uses those thread local variables, that will be, there are multiple implementations possible, but that's one of the most efficient. That's the most efficient implementation on x86. So it's still used, but typically you never see it. Okay, so and then your programming paradigm, instead of like explicitly using those segments, you just infer the segment based on the axis, right? Make sense? We're almost there. So just for a second, what did we achieve with segmentation? Now our programs have an illusion of a private address space. So someone early on in this lecture said, okay, let's virtualize the address space. This is effectively virtualization, right? Because you say, well, each program has address 0, right? So why not? So I have address 0 here and I have address 0 here. But in practice, you know, they point to two different physical addresses, right? Agree? Virtualization, right? What else did we achieve? So virtualization means we don't need to relocate. What else did you achieve with segmentation? It's that's the hardware thing which hardware designers put for you to make your life as a systems designer easier. What were we talking about the whole 1.5 hours? Isolation. Someone whispers carefully, right? So segmentation makes sure that no matter like if it's a move instruction, something inside the EAX register, it only can land, like even if this is like points to FF, whatever, it will never be able to access the upper part of the address space because that will trigger the limit, right? And so there are like things you can wrap around the address space. So if you add like 1 to all Fs, you will land on 0, but it will be your 0, right? So this is where you will land. So there is no way for the program to get out of this, of the physical region allocated for the program by the operating system. And essentially it's contained here. So we are enforcing isolation. Agreed? And it's reasonably fast as well. Remember this 17% overhead, which I keep mentioning, was this move instruction, which we measured on spec benchmarks. Well, if you can imagine that if you're building a hardware pipeline, you can do these checks in parallel, or like roughly speaking in the same cycle as the, like when you do something like move EAX plus 5, this is uses an LEU to compute the address here. But at the same, like after this LEU, you can also like say, look, and we will do another LEU to compute a couple of things, but get the bounds and check the limits, right? So it has 0 or close to 0 performance impact, which is great. So the hardware designers did a good thing for us, right? Agree? Anything else we can think about? What else is there on my slide? I don't even remember myself. So this is an interesting one. We can implement fork. How can we implement fork now? Doing a fork with relocation is nearly impossible. Why is that? we're implementing fork with relocation. Remember, I was pitching for half of the lecture, I was pitching that if I really so love my robot vacuum that I want to run multiple programs on the vacuum, I can do something like a relocation trick. One program starts with 0, another starts from some other address. I can use software fault isolation to enforce the bounds. So I will even get the isolation, but the fork is tricky. So why the fork is tricky? Fork, is it because it's dynamic? What do you mean? Correct, but what is the showstopper?
Oh, I think what relocation happens before.
Correct, that's correct. It happens before the program is even started. But that's okay. Maybe you, if it's a LAS, you can like have a, like fetch a copy from a LAS from disk and relocate it, like before loading into memory, right? We can, but what is the problem? I'm trying to hint at the very specific problem, which is very, very hard.
You have to work like disassemble the whole program, change it.
Kind of. I think you're trying to say what I'm willing to hear. I wanted to emphasize the following problem. Imagine you allocated a data structure as you were running before fork. You allocated a data structure on a heap. Like let's say it's a data structure A, and it has a field which is a pointer P. This pointer P points to, I don't know, maybe it points on your heap, right? So because it's maybe a pointer to a data structure B, right? Agree? You can disassemble of all you like, but you somehow have to go through the entire heap, entire data section, entire stack, and identify all the pointers, and somehow say, look, instead of when you forking and you having an instance of this data structure A here, this P shall not point back to this old heap, but we have to somehow patch this pointer to point to our new heap. And this is impossible in an unsafe language like C, because like there is simply no information about every pointer. You can ask the compiler to preserve enough information, and I would say in most cases it's possible, but there will always a corner case, because in C and other like unsafe languages, there is like no real information about those pointers. In a language like Java, you probably have enough information to identify all the pointers and you can fork. But in this, you cannot. But with this segment, you can, because you don't need to relocate. This has its own address 0. So this pointer can stay the same, but it will automatically point to this yellow heap. Is this clear? It's a kind of an important problem. And I said that I built a couple of operating systems and we never built a fork. And that's the problem why we essentially chose not to deal with it. We didn't have memory virtualization. Okay, last questions. Good. Because everyone is in a low start. Okay, so thank you. Then I will see you on Thursday, and we'll start by saying what's wrong with segmentation. Yep. It's like, oh, just a sec. Let me tweak this. I don't know how. Lost my mouse pointer. Battery is close to 0. Everything. Let me